Now we can talk about precipitation reactions. You've probably heard the term hard water, and you know that they sell water softeners, but you might not know what that means. I mean, the water doesn't feel hard, right? Hard water has dissolved ions in it. Soft water does not, or has much fewer ions. So the dissolved ions typically are things like calcium and magnesium. And the reason the water contains these ions is because it's groundwater. It's come obviously from rain and runoff, but then it trickles through the ground into the aquifers. And as it does that, it dissolves some ionic compounds and picks up calcium and magnesium ions. And these are not bad for you. In fact, they're good for you. You need calcium and magnesium in your diet. But they do cause problems inside of our homes when we're trying to clean things. So hard water reacts with soap and makes a mess, basically. Here in this picture, we can see this lovely gold sink, and it's got this white, crusty stuff on it, right? So hard water will give us hard water deposits, and it'll also give us this soap scum, or this bathtub ring. And it's a compound, an insoluble compound that forms with the calcium and the magnesium in the hard water. Well, it makes a mess in your bathtub, and it doesn't do very much good for your clothes either. It's kind of a gray color, and it makes your clothes all dingy. So laundry detergents, which are different than soap, typically have sodium carbonate in them. The carbonate ions will precipitate calcium and magnesium ions, and as solids, these will come out of solution, and then they cannot form this scum or this curd with your soap. So a precipitation reaction is a reaction in which you have two or more solutions, liquids, that we mix together, and as a result of that, a solid forms. The solid is called a precipitate. Here we have a photograph of someone pouring what looks like water into a flask that looks like it contains water as well. But when these two solutions meet, we have this cloudy orange substance that forms. This is actually a solid, and if you watch it and wait, it will fall down to the bottom of the flask, much like snow. Snow is called precipitation, right? Rain is precipitation. So that's why we call these precipitates. A solid forms, the solid's more dense than the liquid, and so it falls to the bottom. Up here in this solution, we have potassium iodide, and we learned from our study of the solubility rules that potassium compounds are always soluble. So here we have potassium ions and iodide ions. In this flask, we have lead nitrate. Lead 2 ions and nitrate ions. We learned that nitrate compounds are always soluble. When these two solutions mix, the potassium and the nitrate don't really do anything, but the iodide and the lead get together, and from our solubility rules, lead iodide is insoluble. Iodide compounds are generally soluble except with lead 2 and a couple of other exceptions. So we get this solid that forms, and then potassium nitrate remains aqueous. Any questions yet? So here's looking at this reaction again. Here we have our original compounds: potassium and iodide dissolved in water, lead and nitrate dissolved in water. So of course I have a silly analogy for this as well. I've mentioned that I think of metals as being masculine. So these are two guys, potassium and lead 2. Those are the guys. And the nonmetals are non-masculine, so those are the girls, I guess. And so we have iodide and nitrate. And they're going to a party, right? So here we have lead, lead's over there. Potassium and iodide are hanging out together. And they're okay with each other, but there's no great attraction between them. They're just friends, right? And over here we have lead-2 and nitrate, and these two also are friends. They're going to hang out together, but there's no big reaction between them. So they go to the party, and they all mix and mingle here. And when lead sees iodide, there's this immediate reaction, right? They're like attracted to each other. And so instead of mixing and mingling with the other people at the party like potassium and nitrate are doing, these two go off by themselves. This is that couple that ends up like on the back porch on the couch, and they're just like totally absorbed in each other. You don't see them for the rest of the night, right? Because they like each other so much. They're so attracted. Yes?
Why can't it be lead and nitrate?
Well, it could be lead and nitrate, but it isn't. Because lead and nitrate just don't like each other that much. So, and pick any two people. Why aren't they a thing? Right? It's kind of complicated, right? So there is the potential for the attraction between lead and nitrate, but we know from experience that when those two get together, they don't form a solid. They are soluble. And kind of into that whole romantic relationship kind of a thing. Potassium is just really not interested in a relationship. Potassium compounds are always soluble. Potassium doesn't get interested really in anybody, okay? And the same thing with nitrate. She's just not interested. She's got her own agenda going on, and she's going to hang out with people, but she's not going to get into a committed relationship, right? And some people are like that, and that's absolutely fine. So these two are not, they're just, hanging out, having a good time. But the lead-2 and the nitrate together. And exactly why is kind of complicated. So the possible products here, because of the charges here, the only possible products are a combination of positive and negative ions. You can't have two positive ions being attracted to each other because it's electrical charges, right? You can't have the two negatives being attracted to each other. So you have to have positive and negative. Potassium and iodide came in together. They weren't all that attracted to each other. They were soluble. So that's not going to be the precipitate. Lead and nitrate isn't going to be the precipitate. So we're going to swap partners and see what happens. We've got potassium nitrate and lead iodide. How do we know which one of them is the solid? We use the solubility rules. Right? Potassium compounds are always soluble, so it's not this one. And lead iodide, if we follow through the rules, we'll see that this one is not soluble. Any questions? When you mix two solutions of soluble ionic compounds, you do not always get a precipitate. Many times you do not. So if there is no precipitate, there is no chemical reaction. Okay? So in this example, we're mixing potassium iodide and sodium chloride. And so potassium iodide, they come in together, and sodium and chloride come in together. And then here at the party, they're all mixing around together, but no sparks are flying. There's no reaction, right? They're just mixing. So this is not a chemical reaction. Something has changed. It's a physical change. Mixing has occurred, but it's not a chemical reaction. So looking at this, we can write this out as a chemical reaction, but really there's no reaction. Nothing happens. It's just mixing. Only insoluble compounds can form precipitates.
So if it's is it homogeneous?
Yeah, so this would be a homogeneous mixture, a solution. Mm-hmm. So you need to learn how to predict the products and write balanced chemical equations for precipitation reactions. And just to remind you, because I'm not getting evaluated this semester, but student comments are often like, she covers way too much material. That's not my choice, right? You want the class to transfer, right? Because otherwise it wouldn't be any good. So in order for it to transfer, there's this long list of stuff that we have to cover. This is one of them, okay? Whether I agree with it or not, doesn't matter. It doesn't matter if you like it. We just are supposed to learn it. So this is one of those things. So here's a set of instructions for how to write equations for precipitation reactions. You need to start with the formulas for the reactants. So we need to be able to, from names, write formulas for ionic compounds. We need to be able to identify the charges on the ions. And then below the equation, so we're going to start writing the equation, and below we're going to write the formulas of the products that could possibly form. So we're going to separate the ions, and we're going to swap partners and put them back together. We're going to use our solubility rules to see if any of those products are insoluble. If all of the products are soluble, this is what we always hope for because it's faster. You just write no reaction, or we sometimes even get lazier than that and just write NR for no reaction. But if any of the products are insoluble, then you have to finish the whole thing out. You write the formulas for all the products, and you need to indicate their states, solid or aqueous, and balance the equation. So we'll do some examples here. These examples are also going to include a little review of nomenclature. So the equation is given to us in word form instead of as formulas. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate mix. So we need to start this out by identifying what the ions are so we can write the formulas for the reactants. So ammonium, NH4, whoops, don't know how that happened. NH4 plus. If you don't remember that, you need to review your memorization facts. Ammonia is NH3.
What's the charge of that?
0.
Yeah.
Ammonium has an extra hydrogen ion, so it's got a +1 charge, and it's an ion. Chloride, from chlorine, Cl, the charge is minus. Iron 3 nitrate, so that Roman numeral tells us what the charge is. Iron 3. Nitrate, NO3 minus, because I made you memorize it. So those are the ions. Whoops. So I need to write the formulas for the reactants. So I've got NH4 plus and Cl minus. So I look at the charges to predict how they go together, and I just need one of each, so NH4Cl plus Fe3 plus with nitrate. And again, looking at the charges, for 1 iron ion, I'm going to need 3 nitrate ions. We can write the state symbols in here. These are both going to be aqueous.
For precipitation reactions, are the reactants always going to be aqueous?
Yeah, for a precipitation reaction, the reactants need to be 2 aqueous solutions. And now we're going to predict what the products might be. So we're going to swap partners. So ammonium came with chloride. We're going to have ammonium meet up with nitrate and see how that goes. So these two we're going to pair up, and then iron and chloride we're going to pair up. Chemical reaction is like an addition equation in math. 1 plus 3 is 4, 3 plus 1 also 4. The order doesn't matter. So the order, which one you put first in the reactants or the products, is not significant. I tend to just take this first cation and make that the first one in my products, but it doesn't really matter. So I'm going to put NH4 plus with NO3 minus. And then I'm going to pair up the other two, Fe3 plus and Cl minus. By convention, the cation is always first. Just like a formal invitation is always Mr. and Mrs. Regardless of how you feel about anything, that's just how they do it, right? Positive, negative. So these two, are they going to form a soluble compound or an insoluble compound? Think about that solubility rules list. It's going to be soluble because the first row, ammonium, lithium, sodium, potassium, always soluble. So this is soluble. Iron 3 chloride. Well, we go down the list a little bit. We've got the cations I just mentioned, and then we've got nitrate and acetate. That's not in here. And then we get to iodide, chloride, and bromide, and those are soluble except with certain things. Is Fe3 plus one of the exceptions? No, it isn't. So this is also soluble. So this one is no reaction. We had to do a fair amount of work to get there, but any questions? So if I mix these two solutions, it's going to appear that nothing has happened. No solid's going to form. We're just going to mix, and that's it. Let's do another one. Write the equation for the precipitation reaction, if any, when sodium hydroxide and copper 2 bromide mix. So we've got our reactants, sodium hydroxide, copper 2 bromide. I can save a little bit of writing by just figuring out those ions down here. Sodium is going to be Na plus. What's hydroxide? OH minus. So my one reactant is going to be NaOH. Is that aqueous? Yeah. And my other one is going to be copper 2 bromide. So copper 2 is Cu2 plus, and bromide is Br minus. So this formula is going to be CuBr2. I have 2 bromide ions. I'm not going to put parentheses around them though because it's just a single ion and it's not confusing. Soluble or insoluble? This is going to be soluble because if we look at those rules, bromide compounds are soluble with a few exceptions, but copper isn't one of them. So this is also aqueous. Now I'm going to predict my products, and I'm going to look at how do these combine, swapping partners. So the first possible match is sodium and bromide. Is that going to be soluble or insoluble? Soluble, right? Because sodium compounds are always soluble. So this one's aqueous. And the other combination is Cu2 plus and hydroxide. On that list, as you go through the first part, you're not going to find copper 2 or hydroxide in the top part of that table. Hydroxide's in the bottom part, in the generally insoluble. There's some exceptions, but copper is not an exception. So copper hydroxide is a solid, it's a precipitate. So this is our solid that's going to form. So we do need to finish out this equation. I'm going to use the charges on these ions to write the chemical formula for that. And then Cu2 with hydroxide, I need 2 hydroxides, and that's going to be a solid. Any questions so far? We're not quite done. The last thing to do is to balance the equation. These equations generally are easy to balance, provided you've got your formulas correct. over here I have one sodium, and here I have one sodium. Here I have one hydroxide ion. Over here I have two hydroxide ions. So I need to put a 2 in front of sodium hydroxide. So that fixed the hydroxide, but it messed up the sodiums. Now I have 2 sodiums, and over here I only have 1. So I can put a 2 in front of sodium bromide. Now I have 2 sodiums. Copper, there's 1 over here and 1 over there. Bromide, 2 and 2, and there we go. Any questions? Yes?
So if something is insoluble, and I was thinking it's soluble, it's aqueous?
Yes.
Can it be aqueous and not insoluble?
No. So a solid is insoluble. An aqueous solution is soluble. What's a little confusing is that solid and soluble both start with S, and so we have to remember what this S is standing for. Now, this is in context of this precipitation reaction where we have solutions. Can you have solid sodium hydroxide? Sure, but if you put it in water, it's going to dissolve. Any other questions?